All right. You can either create a new project, or you can use an old project, by which I'm going to use an old project. So even though I have churn here, and this project is for the telecommunication company, it really doesn't matter that much, because I keep every data set in the same folder. I like to use the same library, and that's it. So I'm going to create new data source and new diagram, and build the project here as if I'm creating a new project. So the first thing is to create the data source. The data set is classify risk. You all have the data set, right? Do you have the data set? You can download it from week 5 folder. So I hope you can follow along, because this will be almost what you're going to do in homework, although it will be on a different data set. So I can use the basic metadata, and we'll take a look here. So first thing is we have to decide which one is the target. So the risk here is a target. And although it's binary, but being nominal would be fine. Mortgage is nominal, binary, same thing. All the others, number of loans, is nominal. Yeah, it's according to the PDF, it's changed them to nominal. But something is happening here for let's see, for the k-nearest neighbor algorithm. It's called memory-based reasoning, MBR, memory-based reasoning. So this algorithm in SAS doesn't take into account the nominal variables for input. So for MBR algorithm, as well as for your homework, the standard approach would be to let the model only use interval variables. So here there are only 2 interval variables here, right? So the model will really only use 2 of that input variables, as well as the target. Huh? Do you have that? Do you have this week's PDF, the MBR? Yeah, you can do according to that. So confirm that you have 2 interval, 1 or a bunch of nominal. Okay, now you can create a diagram. So a couple of things to keep in mind. Usually you would do, and in the same case here, we would do Static Explorer to understand you know, the basic statistics and missing values. And we'll do that. But let's see, before that, I would also include the intervals as the variable worth, and then we'll run. I changed the chi-square stats for interval as yes, that's the floor, yeah. So review the missing values. There's no missing values. There are let's see, 123. So there are 246 total points. 123 are good credit, 123 are bad credit, so 50-50 split. No missing values for the nominal variables, no missing values for the intervals, so which is great. And that's it. Well, take a look at the rank. The income obviously is shows up to be the most correlated variable to the target, and same rank here for income, although different heights of the bars, but roughly similar, right? The order in which the correlation of the inputs are: income is the most correlated, age is the next, and marital status and loans, although the middle three are relatively similar. As for loans, number of mortgages doesn't indicate too much about the credit risk. Okay, now for a supervised project, normally you would do the partition to enable the cross-validation. For this homework, you won't do it because you only have 10 points, right? And you need to answer questions about the 10 points. So you will skip the partition, data partition. And that's what I'm going to do here. I'm going to skip the data partition. And we will do the MBR model, memory-based reasoning. But before doing that, there's a critical step you have to do, is to standardize the variables. You know, standardization makes the scale of the variables doesn't matter. So sometimes the variable has large ranges, like income, from 0 to maybe 1 million. And sometimes the other variables may have smaller ranges, like age, ranges from 18 for this data set to maybe 100. So smaller windows. The scales of the variables make a big difference in terms of calculate distances, right? The original scales, the variables that has wider ranges will have more weights, will be more influential when you incorporate them in the distance calculation with other variables. But you don't want that to happen. You don't want the scale to make a difference. You want the scales to have the same influence. So you need to standardize the ranges of the different variables. Well, that's when you use the standardization tool. Do you remember where the standardization tool is? Which node is it? Yeah, it's a very powerful, useful node, right? The data transform variables. Right. The first thing here is, we'll go into formula and take a look at the distributions. And we may have to update or run the node before we can see that. where we can see that. So the first thing to look at is income. It ranges from 15,000 to 78,000, a somewhat narrower range than I would expect, but because this is a smaller data set, this looks normal. You know, more concentration on lower ranges, and a right tail skewed distribution to the right. They all look very normal. In terms of age, it's fairly normally distributed with the symmetric tails and concentration in the middle, but still a wide distribution. So all of these good. Marital status, there should be 2 or 3 categories, and look good. More singles than married. Others include divorce and other things. Number of loans between 0 and 3 look normal. Number of loans means the number of currently effective loans. So how many loans do they have currently are liable to? Number of mortgage, yes or no? Do they have mortgage as well? And this data set is to predict the risk of mortgage default. So having a mortgage concurrent, maybe indicative. But as we see the rank of the variables, mortgage doesn't make much difference. Okay, so the point here is really to review the distribution to identify any problems, right? If there's no big problems here, then you will standardize the variables. But keep in mind,
Dr. Wall, could you please click back on classify risk? No.
Classify risk, yeah. So what information are you trying to see?
Oh, just to see what changes you made.
I didn't change for the data source. Yeah. So it should be fine as long as you drag and drop. For transform variable, you don't want to change anything else for now because you didn't see any other problem. The only thing you need to do is to standardize the ranges. So you make sure that every default methods is turned off, no default methods clicked is effective. And something I forgot to do, and it's not too late to do that. Make sure I have a random and max for the sampling. And rebin, that's fine. We'll look at the data set distribution, that everything looks fine. So then now it's time to go into the variables to choose specific standardization. For nominal, it's not possible to range standardize. It's only for the interval. Right, for the 2 interval variables, I will select them and I will do a batch change modification here. I will choose a range standardization. What it does really is to make sure the 2 variables here, the age and income, after transformation, the values of these 2 variables both have minimum 0 and maximum 1 after the transformation, so that their arbitrary scale don't matter much. The arbitrary scale should not be incorporated into the distance calculation. So that's why it's very important to do that here. Make sure you click you confirm, you click OK, and you can run. Review the results. Make sure that the variables that are supposed to be transformed are indeed transformed. So you can see what happened in the background. So the 2 original variables are transformed, it has a range prefix. That means range standardization. So this is the formula that's applied to all the values of age and become the range age. So it takes the age and subtract by 17. What is 17? 17 is the minimum value. It's the floor, if you will, the floor of this variable, right? If you subtract all the value by 17, then you make sure the minimum after transformation is 0, right? That makes sense? And then the denominator is 66 minus 17. 17 is the minimum. What is 66? That's the max, right? So then you divide the difference by the range. It makes sure the maximum is going to be 1.
So it's going 1 by 1, 17 minus 17 divided by...
Yes, 1 value by 1 value. Yeah. And the same thing for income, except that the minimum and maximum changes in this case. It's a much wider ranges. But after transformation, it becomes 0 to 1, right? So that's good. All right, now you're ready to apply the model. Under model, it's a very white tile with points and curve in it. Yeah. Let me make sure. There's a caveat to this node. Very weird behavior. So let's say when you calculate distance between a point with all the other points, that that point with question mark, you can still count that point as a point, right? So hypothetically, you can always find the closest point, which is the point itself. It's the self-image, if you will, in the data set. But we're not supposed to include that because that's the same point. That doesn't make sense. That happens for all the points. So by a better way of implementing k-nearest neighbor is to not consider the point itself and only consider the other points, right? By including the point itself, it incorporates a little bias, which is the label of the point itself, which is the bias, right? It's biasing toward itself, which doesn't make sense. But SAS automatically include that point as one of the k. So if you say we want k equal 3, meaning 3 different points, but then if you say k equal 3 here, it will only count 2 other points, and then include the point itself. So, but you really want to counter that bias, so you would include 1 more, right? If the question asks for 3, you would choose 4. So always increase by 1, just for the problem's sake. Here the number of neighbors is the k, right? So if the question asks for 3, you would use 4, and you'll see the 4 points, which include the point itself. Question? And then not much. This algorithm don't matter that much. It changes slightly the calculation of the distance. So that's when you are ready to run. Create these are default settings, and it's fine to keep them. Create neighbor variables, meaning for the output data set, you'll have extra columns to indicate which neighbors are the closest neighbors to this point, right? If you ask for 4 neighbors, it will create 3 more columns to indicate the neighbor 1, 2, 3, right? So you need this information because you need to answer that question in the homework. So I'll skip these graphs. These graphs will be useful after we talk about it. The concepts such as lift, gain, cumulative, they will be talked about in toward the end of the model evaluation stage. So the main thing we do here is to confirm that the model ran and to look at the summary of the results. Model events. So the target variable is the risk. The meaning of that, the label of that variable is good risk or bad. It's just the meaning of that variable. There are two levels. Number of levels are 2. Descending meaning, the larger value means the good risk, basically. Anyway, so this confirms that the model runs. To answer the question of which neighbors are the k nearest neighbors of a particular point, you need to go into the exported data set. Do you remember how to get to that? So once you get there, you'll browse the data set, right? Where do you find the exported data set?
MBR.
Yeah, MBR.
And then export data set, you click the 3 dots.
Exactly. And there's only one partition here, right? Because we didn't do partitions. So you'll find all the points here. So click that MBR. You want to extract the data set after running this model, right? So exported data, you'll see a list, and you can only find one data set that's available. You'll click that, and then you'll browse the data set. So this is the data set. Look at and it does have other like reporting related columns like warnings and some other contextual information about the model. So a little bit explanation here. So this is the column where the prediction is made for this observation. Observation number 1. Prediction label is 1, and the label of 1 means bad risk. Is a primary outcome that it's interested. In this case, the predicted value of the outcome is bad risk, not good risk, because bad risk has a value of 1. It's predicting bad risk, not good risk. And comparing let's see, residual, nearest neighbor, and you have the outcome this is the actual outcome of the original data, right? This case is actually bad loss, is bad risk. That's the actual outcome. But when you apply the k nearest neighbor, it ignores its own label and try to use the other neighbors labels to predict this point. So based on those neighbors, the prediction was also bad risk. So there's no residual. And here are the nearest neighbors. The nearest neighbor include the point itself, as I said. The algorithm always does that. Other than that, there are 3 unique neighbors. The neighbor number 4, 44, and 90. And at least 2 of them are bad risk. So that's why the majority vote will give you the bad risk prediction. Right? We can check that. Number 4, 90, and 44. Number 4 is bad loss, is bad risk. And number 44 is also bad loss, so at least 2 votes, right? And number 90 is also bad loss. So, you know, it's a unanimous vote for the bad loss situation. And are they all bad loss? Not necessarily. These points are good loss. So points close to these points will be assigned good loss based on k-nearest neighbor algorithm. Does it make sense? Does it give you a good visual illustration? So this is almost, you know, how your homework process will be if you haven't done it. Any other questions for k-nearest neighbor?
I noticed like everyone can have like different values for nearest neighbor. That's normal, right?
Everyone, you mean every row?
It's like,
Not like us.
With your, you sure?
Like ordered by like.
Yeah, when you order things, then the different rows are for different value points. Yeah, if you want to really compare different projects on the same data set, then you need to make sure you have the same sorting mechanism, right? You have a ID column to identify the same point, and then you can compare. Any other questions? We're good? Yeah? I can close this diagram. All right. So for k-nearest neighbor, there are some illustrations in the slides. You can review them. They are fairly, fairly consistent with the book. They're just, enlarging some of the contents here. By reviewing the slides, you get some, confirmed view of what I just went through, and I think that would be helpful. It explains why or how the standardization is done in the slides, and you can confirm that it's subtracting the value by the minimum and divided by the range. And that's range standardization, and you can go beyond simple voting, like simple majority voting, and you can incorporate some weighting mechanism for each vote. And intuitively, you can use the distance as the inverse weight. You can use the inverse distance as the weight, because it's intuitive to say that points closer to the focal point should have a better weight because it's closer. So points that are closer to the focal point in the k points, its label should have a better influence on the prediction. You can make a good argument by that, because that's the same principle of k-nearest neighbor. The argument is that the points closer to the focal point should decide the prediction because they are closer on the features. So by the same principle, they should carry more weight. And you can apply a good mechanism there by assigning different weights there. And the slides will talk about these. All of these are happening in the background of SAS. And toward the end, I want to show you the the overfeeding graph. So this one is more of a simulated one rather than based on the example I just demonstrated, but it will be consistent with the picture that you would have gotten based on the data. So with the blue line being the training set, as you zoom in, you start out with a very large K. So what that means is you base the prediction based on the entire sample. A K as large as the sample size would be the largest K you can have. Based on the average value of the label, the target, you will assign the typical value to every point. You'll definitely make some mistakes, right? But this is the overall sample average. Then in that case, you probably make 40% of the errors, mistakes. So as you shrink the K, you are putting the lens closer and closer to the focal point. You're excluding those points farther away from the focal point, and you're using the closer neighbors to predict the question mark. You can imagine that it's becoming more relevant, right? So the performance should increase both in the training and in the validation, because naturally closer points are going to be more informative overall, right? So as you reduce the K, the performance in terms of error rate on both the training and validation will reduce. So that's good, right? But before long, you'll hit that point where the K is too small. It's focusing on too small of a region where it's generating too, peculiar predictions because it's overfitting, right? K is too small, it's overfitting, it's relying on more local randomness than more of a pattern close by. So then the validation set error will start reversing, while the training set error is going to reduce still, just because it's using the training set labels to predict. And to the extreme, if you have K equal 1, you're going to make a perfect prediction because you are using the point itself to make predictions. So then, it makes perfect model prediction in the training set, but then a horrible model in the validation set. So same mindset. I hope that makes sense. All right, so I'll repeat that story over and over. So that's k-nearest neighbor. So let's take a short break, don't leave the seat, but 2 minutes. We'll transition into the decision trees. All right.
I live on campus, but I'm too lazy to go predict the shows. Technically, I could take the bus.
So decision trees. Decision trees mostly good at classifications. Same thing with the k-nearest neighbors, is to predict the label, predict the nominal variable. It can also be used to predict interval variables, target variables, but it can get weird in some cases when the leaves are very small. Yeah. So supervised versus unsupervised, it's a supervised, just to and be aware of the overfitting. And overfitting, you'll see a similar graph with the overfitting lines, but the x-axis will denote a different let's see, a different feature about the model. For k-nearest neighbor, the x-axis is about k, and how large is the k, and k goes smaller from the largest. When k is the largest, it's the simplest model. For trees, it's the size of the tree. It's how many leaves are there. We'll take a look at the tree. So this is a simple tree in SAS's annotation, in SAS's graphic interface. It's an upside down tree. It's a magic tree, upside down, where the root is on the top. It starts from one node and it branches out. A couple of features you can see here. Based on twofold cross-validation, you always have two columns for the statistics. You have a train and a validation. The validation is shown to you to let you see the differences. The bigger the difference, the stronger the signal of overfitting is. But that's about one leaf, and that's not the whole story. You need to look at the entire tree to see, how much overfitting is happening. And typically, as you go toward the root, which is the upper portion, overfitting is less likely because it's the first split, it's the first part of the growth. And the model is good at picking up the most important predictive features. So those are not likely to be overfitting. As you go deeper and deeper and go into the upside down branches and leaves, you start to see overfitting. So decision tree gives you a very graphic view of the different portion of the predictions, and you can see the overfitting from there. Depending on the setting of the model, you can sometimes split into two branches every time, or you can split to more than two branches. So that adds more complexity to the model. What is the thickness of the lines? Some lines are thicker, some lines are thinner, and some lines are darker, some lines are lighter. The thickness of the lines, the branches, you only start to see differences when it branches out. Indicates the relative percent or relative number of observation going into that branch. So if you have a split that makes two very different size splits, with one branch having 10% of the sample, the other branch having 90%, you'll see a dramatic difference in the thickness. And the reason why it's splitting this way versus alternative ways, I'll explain shortly. But just so you know, and with the bigger, let's see, with the bigger branches, it will show a black box, thicker box around the branch. So every box is called a node. Every sort of the separation is called a split, and then after the split, it's one branch versus the other, and the branch will further split. Right? That's how the tree grows. So yeah, what is a split? A split is a rule, is a decision rule that separates the sample into, in this case, two branches. It's unequivocal. It's unambiguous decision. It separates the branch, this branch, the root branch. It separates the branch into two mutually exclusive sets, right? And based on one feature, based on one variable. In this case, this is the donation data set, right? The most informative variable is the gift count, 36 months. It's the number of gifts that the person has made within the past 36 months. And that's the most informative variable to split first on the entire sample. And if this variable is smaller than 2.5, it goes to the left. If it's larger than or equal to 2.5, or if the value is missing, it's included on the right branch. So you can see that focusing on the training, the original data set has 1,813 points. After the split, the left branch has 48, sorry, it's 4,843 points. After the split, it has 2,283 on the left and slightly more on the right. And still within the training, the overall sample has fairly balanced outcomes, right? With the 50% having the target label 0, which is non-donor. 49.99% having label 1 for the target, which is a donor, right? And after the split, look at what happens. For the training set, 57%. For the left branch, 57% are non-donor, and only 42% are donor, as versus on the right, you have majority donor than non-donor. So based on only one split, you're better able to predict. You make fewer mistakes, right? And same thing on the validation. It used to be evenly split in the two outcomes. After one split, you have fairly consistent values, right? If not identical. And the difference is because of randomness. The consistency is because this split is a good split. It leads to better model. It didn't lead to overfitting. Do all of these make sense? All of these make sense? Great. So then you will make more splits. But know that, based on the procedure of the decision tree, the first split is almost always the most informative split. It almost always doesn't lead to overfitting in the first step. As you go down, overfitting becomes more likely. And you can imagine as it goes down, the sides of each node becomes smaller because it's branching out over and over and over. As it gets to a point where the node size is too small, you can't really trust the prediction there because it's too much deep into the local patterns. That's when overfitting likely will happen, right? So you have a good understanding of the splitting rule. If you see this split with all the branches, with all the nodes before and after, you can write out a clear decision split, a decision node, right? A decision rule, that's what we call. A decision rule focuses on how the split happens from one branch to two branches. And you would describe a few elements here. The if condition is the feature by which the split happens. The level of the split, so the if condition includes that too. Which variable and which level. And then if it's if-then. If it's on the left, what happens? If it's left, it goes there. This many predictions are based on the majority vote. That makes sense? Right? On the left, everybody here will be predicted non-donor because the majority is non-donor. Yeah. By no means this is a final prediction, but at this point, the decision rule is like that. Questions? We'll go to the demo from this point on. So this is an illustration of one decision rule. Okay, so let's do the demonstration. We will use a different data set. We'll use the PVA97, which is the donation data set, but with a different name. So we'll simply use this new data set. So same thing, we'll create a new data source. All right, I may do something here. Missing percentage 50, 20, reject. Class level state. Class level. Maybe good. So the first thing is to revise the target. We need only one target, one and only one. We'll keep the B, target B, which is the donation yes or no decision. We will reject the other target. Wait, hold on. Does your power work?
Yes.
Yes. Yeah, I need to borrow that. It's not working here.
So, like, I'm using the one over there because this one doesn't
I'm
work
using
for
this
me.
one. Oh, you did?
This one didn't work for me, so
Oh, it worked for me.
let's see.
So we have the same.
Great. Thank you. All right. Let's see. So quickly review these variables. Nothing is being rejected, which is great. Status. Target B, target E, damage. Question?
Oh, it's not on.
Oh, it's not on. Okay. All right. Great. Good call. So I changed a few metadata rules, which may, result in different levels here. Just let me sort the name. Let me sort the level. And there are only 3 binary, so make sure you have the same 3. And a lot of intervals, starting from the gift and some more gift here, and the promotion are all intervals. The nominal ones include the ID and status, gender, gift count 36. It's nominal because there are only very few unique values. But gift count 36, I will still convert it to. It doesn't allow me. I don't know what. Or a cluster. Count 36. I would change it to interval. This one, promo count card interval. For decision trees, this probably don't even matter because the way decision trees calculate different splits. I'll talk more about that. It's actually what I'm doing here for these sort of wrongly designated level variables, they practically won't matter even if I change it. And you'll understand why when I talk about the split rules. So the only nominal variables left are the ID, cluster, status, and gender. Right? Decision rules, we would have decision rules in donation cases because, right? Because the two decisions would have different cost and benefit. But for now, we'll keep it simple. So now I'll create a diagram decision tree. So I only have 3 minutes. So let's do an interactive tree growth, and let me explain the backend. Drag the data set. So to save the time, I'll skip the Stat Explorer, but you understand what we were supposed to do with the Stat Explorer, right? But here I need to do the partition because that's going to be important. The cross-validation part, it will be under sample, cross-validation, data partition. And let's do a 50-50. Or yeah, let's do 60 and 40. Okay, and then the decision tree looks like a tree. So let me edit the name. And at least I would need to run until the data partition. So review the partitions. We focus on the proportion of the donors versus non-donors in the three sets. In the overall data sets, 50-50 split. The same thing in the two partition sets. So as far as the distribution of the target, it looks very well. And you see more data point in the train set because I set 60% for the train. So that's all good. Everything's good, following along. There's one more thing to do. So here, with the tree, let's go to the interactive. So you see a roof node there. You cannot drag it. Similar view, you have a training and validation set. It's 50-50 split of the outcome on both, as you saw previously. You have more data points in the training set because we set 60%. And you can, manually, you can interactively split the first node by going split node, it will give you a contextual menu. So this one illustrates how it's split. What are these? These are different variables and labels. Label the variable. And so you have give count 36, give average card, I don't know, gift average last, and things like that. For the different variables, it calculates a informative value, stat here, statistics, minus log p. What does it mean? It simply means the variable worth. So the bar graph that you see in the Static Explorer, it's based on the values here. So the average, the gift count 36 would be the first bar because it has the highest minus log p. So what is minus log p? It's some transform version of p. But what's p? P is a p-value of a chi-squared test between the input and the target. A chi-squared test basically tests correlation, but it's a correlation measure that can extend to nominal variables, right? It's different from rho, which is a Pearson correlation. The Pearson correlation has limitation because it only applies to interval variables. You know, a lot of times we make predictions, we make classifications. The target is binary, and sometimes nominal. Sometimes have more than 2 levels, and those 1 and 2 levels cannot be ranked. So without the ranking, without the ordering of the data, you cannot use rho, Pearson correlation. So you have to use something else. Chi-square is a more generalized version of the correlation measure. Now once you have the correlation, you have a p value of that statistic. You know, with the conventional statistical testing, the larger the statistic, the smaller the p, right? The larger the statistic, which is the chi-square, the more, the stronger the correlation is, and the smaller the p is. So that just means, you know, a better correlated variable, but you have a smaller p. So you have to reverse the scale. The minus sign is here to reverse the scale. And taking the log is making the p larger to be more clear. So then that's all the transformation you need to do. You know, just rest assured all those transformations make sense to the mathematicians, and we just trust them. But after all the transformations, you have, you know, these nice values that are discernible, that they can be differentiated. And this table ranks the variables according to the minus log p. So it's a list of ordered variable importance, basically. Right? The first variable appear to have the highest correlation with the target. So that would be the ideal split rule feature, right? But still, every variable has multiple values that you can split the sample, right? Let's say for gift count 36, there are people who made 0 gift within 36 months. There are people who made 1. There are people who made 2. To split the sample, you can split by 2, lower than 2 or larger than 2, or equal to 2. You can use 3, you can use 4. Which value does it pick? SAS will calculate every alternative and compare the log p and retain the strongest one. And here the strongest one is 2.5. So SAS has done all the calculation for you, and it has retained the optimal split value for each of these variables here. Right? So thousands of millions of calculations in the background you didn't see, but SAS is powerful enough to have no delays and just show you the result. right? So interactively, you can also revise the point. You know, if you go to edit row, you'll see the split point, which is the optimal point of split by SAS standard. But if you somehow say, you know, that doesn't matter, I want to change, so you can change. You can change it to 3, something close, something that makes it easier for your business to make decisions. You can do that. But you know, know that when you revise the values, you are not, you know, taking the numerically optimal decision. In sort of saying. So I'm going to accept that, and if I say apply, it will split based on that variable and that decision rule. And you know, this is the same picture that I showed in the slides, right? So as far as this tree goes, it's a very simple tree. The results are consistent across the 2 partitions. There's no overfitting detected. When you do the graph, you can see clearly the error is reducing for both partitions. So I don't have more time. We'll continue next class. We'll have the midterm in 2 weeks, right? Yeah. So Friday is the homework 3. It's about k-nearest neighbor. And any other questions?
How is the quiz gonna be, or the tests? What do we need to study for the tests?
I'll talk about next time. So don't be stressed. It's the only thing to know is don't be stressed.
Now.
So I shouldn't remind you to be stressed. No, don't be stressed.